Good evening, friend. It's good to share this quiet with you. Perhaps the day asked a bit too much, or you just want your thoughts to drift like a small tide. Let your shoulders soften. Let the room feel simple and kind. You are safe here, with a soft voice and a steady breath to keep you company. Tonight we slip a gentle question under the pillow. How fast can we really go before the rules of physics ask us to slow down? We will wander from walking pace to highway breeze, then to jets, rockets, and the bright shoreline of light itself. Along the way, time will stretch in curious ways, distances will change their shape, and speed will turn into a quiet conversation between motion and reality. No hurry, no heavy math. Just clear images, careful steps, and pauses where the mind can rest. If this calm journey brings you ease, a light touch on, like and subscribe, helps other late-night listeners find their way here too, only when it feels right. For now, breathe a little deeper, close your eyes if you wish, and let the night carry us forward. Out beyond the last weather reports and the last air traffic, there is a small, patient machine that has been flying for nearly half a century. Voyager 1 moves through a darkness that is not empty, a faint sea of atoms and magnetic ripples gliding at about 38,000 miles an hour. On paper, that number looks heroic. In the body, it feels like a hush. At that pace, the nearest star is still 70,000 years away. A journey measured not in calendars, but in languages we have not yet invented. Speed that would blur a city into a single light becomes a soft crawl against the scale of the night. To make the sizes feel honest, let the mind shrink the world. If Earth is a blue marble in your palm, the moon becomes a pale pea resting a foot away, patient and familiar. Mars, when it swings closest, is a smaller marble 30 feet across the floor. The sun is a warm beach ball down the block, 400 feet away, filling the room with light you can almost feel on your face. And Proxima Centauri, the nearest star beyond our own, would be another beach ball not in the next room, but a full world away, about the distance around the entire Earth. That is what our fastest machines are up against. Not a wall, but an ocean of space where distances are the story. Our first bold steps showed how even nearby goals take steady patience. The Apollo crews took about 3 days to coast to the moon after a hard push that touched roughly 25,000 miles an hour. That shove is called the translunar injection, and it feels like leaping from a dock into a slow, curved river. The rest of the trip is quiet drift, while gravity draws the arc. Faster than any jet, faster than any bullet. Yet compared with the map of the sky, it is a calm crawl you can hum to, a lullaby paced by radio checklists and the soft ticking of onboard timers. Closer to the sun, speed has a different music. The Parker Solar Probe dives again and again toward the bright furnace, borrowing a little momentum from Venus to tighten its path. Near its closest swoops, it reaches roughly 430,000 miles an hour. New York to London would be a half-minute errand at that pace. The record lives there, in those hot ellipses where sunlight turns instruments into brave, shielded seeds. And still, even with a speed that turns continents into commas, a journey to Proxima would take thousands of years. Light itself needs more than 4 years for that crossing, and light has no luggage, no fuel tanks, no worry about slowing down at the end. Voyager 1 and its twin learned a beautiful trick to reach such far corridors. Gravity assist is the quiet art of falling with intent. The spacecraft do not simply pass the giant planets. They fall toward them, trade energy the way skaters push off each other's hands, and leave with a new heading and a handful of extra miles per hour. Jupiter gave the first pull, Saturn the second. Each encounter was a bend in a cosmic pinball lane where every bump makes you faster. It is not stealing. The planets lose an imperceptible fraction of their vast orbital energy, a cost so tiny that only the math notices. In return, a small craft gains a path to the outer darkness without carrying mountains of fuel. Even conversation with a traveler that far becomes a lesson in scale. Voyager is now more than 15 billion miles away. Signals leave Earth at light speed, a radio whisper inside a tight beam, and they still need almost a day to arrive. The machine hears, thinks in its simple way, and answers. Then we wait again. It is like talking across a canyon and letting the echo take its time. Mission teams plan commands with that delay folded in, a slow table tennis match that rewards patience and precision, a rhythm of send, breathe, receive. Another messenger, New Horizons, showed how a fierce start does not guarantee a quick arrival. It left Earth in a clean, hard arc at about 36,000 miles an hour, swift enough to cross the moon's distance in 9 hours. Even so, the path to Pluto required 9.5 years. Not for lack of courage, but because the solar system is large and the laws are steady. The closer you are to a destination like Pluto, the more gentle you must be with your final speed, or you will flash past the target with a single, stunned photograph and a regret you can never catch. Travel is not only about going fast, it is also about being slow at the right moment. The way we make speed in space begins with a simple rule. To go one way, you must throw something the other way. Rockets are tidy lessons in Newton's third law. Chemical engines like those that lifted Saturn V are controlled thunder, flinging hot exhaust backward so the rest can move forward. They are strong but hungry. Most of a rocket's weight is propellant, and much of that propellant is burned just to lift the propellant that remains. It feels like moving house while carrying the house on your back. The beautiful curse has a name, the rocket equation, and it whispers the same truth every time. If you want a lot more speed, bring a lot more fuel to push the fuel you brought. So we tried a different flavor of patience. Ion propulsion trades violence for finesse. Instead of fire, there is a blue, quiet, charged atoms nudged to extraordinary exhaust speeds by electric fields. The push is so gentle, you could resist it with a sheet of paper, yet it never gets tired. Day after day, the small thrust adds up, like the steady pull of a tide. A craft like Dawn used that whisper to visit Vesta and Ceres in one mission, circling one world, then unspooling its orbit and circling the next. The trick works best when you have time to spare and sunlight or a reactor to feed the thrusters. It is the art of letting patience become propulsion. For humans inside their ships, our fastest moment came on the way home from the moon. During the Apollo 10 return, the capsule skimmed Earth's gravity well at nearly 25,000 miles per hour, about 7 miles each second. It is a number to make the heart skip, and yet, stretched across interstellar space, it becomes a long lullaby. Even if that pace could be perfectly held toward Proxima, the trip would last on the order of 100,000 years. To fit such a journey into a human lifetime, you would need thousands of times more speed than Apollo could carry, and you would need to keep that speed kindly under control. Sunlight can also be a hand on the back. Solar sails spread a bright skin to catch photons. Light has no rest mass, but it carries momentum, and when it bounces, it nudges the sail forward. The push is tiny, like moving a ship with ping-pong balls, But in the vacuum, there is no friction to undo the progress. Japan's Ikaros showed the idea in the light near Venus, and later, light sailcraft learned to turn and tack. Farther from the sun, the pressure thins quickly. At Jupiter, the push is about 1/25th of what it is near Earth. To climb to great speeds, you would want sails as wide as city blocks, yet thinner than tissue, a fabric that can fold, survive micrometeors, and hold its shine. The engineering feels like origami made of starlight. There is a bolder thought that uses light made by us. In one sketch, a fleet of gram-scale probes wears tiny reflective sails, while a ground array of lasers pours a river of light into them. With enough power, the little craft could surf that beam to a fraction of light speed, perhaps a fifth. A 20-year crossing to Proxima becomes thinkable for a chip that weighs less than a swallow. The price is difficulty. A laser system drawing the output of many power plants must hold a tight focus across a great distance, shepherd the sails through the first violent seconds, and protect the ground around it from its own brightness. The probes would carry cameras and sensors fit for a postage stamp, brave and small and many, so that a handful might survive the long shot across the dark. Between the gentle and the audacious sits the quiet heat of nuclear ideas. One path uses a compact reactor to warm a propellant, doubling the efficiency of a chemical engine. Another uses a reactor to feed electric thrusters, pairing endurance with higher power. Both make the inner solar system friendlier. A trip to Mars could shrink from many months to roughly a season, a change that matters for bodies and minds, for food and repairs, for patience held over long days. There was once an even wilder blueprint that proposed riding outward on the repeated shoves of nuclear pulses against a strong plate and a forest of shock absorbers. The physics smiles at the idea. Treaties and good sense ask us to be careful. We keep the knowledge, and we look for gentler ways to use it. Talk of high speed brings time itself into the conversation, though for the machines we fly now, the effect is faint. Clocks that move quickly or sit higher in a gravity field tick a shade differently than clocks on Earth's surface. The satellites that guide our maps and phones feel this by tiny amounts each day, about a few dozen microseconds. Engineers correct for it so that routes stay honest, and fields, hospitals, and runways get where they mean to go. The dilation is real and measurable, proof that speed and gravity tilt time a little, but at our present velocities, it is a subtle bend, not a magic doorway. Even before a rocket leaves the pad, the sky has opinions about when to go. Planets move in their own slow dances. To meet another world kindly, you wait for a window when your starting point and your destination lean toward each other. For Mars, that sweet geometry comes around roughly every 26 months. Launch too early and you chase a retreating partner. Launch too late and the path grows long and wasteful. Hitting the timing is like stepping onto a moving walkway that happens to be aligned with your goal. Miss it, and you can walk very hard and still arrive tired and late. Once underway, every pebble of gravity matters. Planners draw paths that account for the pull of the sun, the helpful tug and mischief of Jupiter, and the lighter hands of the other giants. A small error at the beginning becomes a big frown 100 million miles out. So the math is quiet and exacting, tuning angles and times down to fractions of a degree and minutes, knowing that a clean arrival years later begins with those early whispers. Mid-course corrections are like small taps on a steering wheel to keep the car aligned with a far white line. The art is to make the taps gentle and rare. One graceful example lived around Saturn. The spacecraft we called Cassini took 7 years to reach that ringed lantern, not because we could not go faster, but because entering into a long dance requires modesty at the door. Cassini toured gravity assists first, twice past Venus, then a return by Earth, then a deep hello to Jupiter. Each meeting added a twist, a bit of speed, a subtle change in the tune. The meetings had to be timed like music. A few minutes of slip at Jupiter would have meant missing the rendezvous with Saturn years later. When at last the craft arrived, it turned and lit its main engine for a burn that lasted more than an hour and a half, surrendering enough speed to be caught by Saturn's pull rather than slinging past into the cold beyond. Speed in space is not only about getting there quickly, it is also about being able to stay. Cassini reached Saturn moving more than 40,000 miles an hour relative to the planet, and then had to give up thousands of those miles per hour to be captured into orbit. The fuel for that surrender weighed a great deal. If we had insisted on arriving sooner, we would have arrived faster, and then we would have needed even more fuel to slow down, fuel we could not afford to lift in the first place. The rocket equation nods again, reminding us that haste is expensive, and that careful arrivals are as heroic as fast departures. We carry a single, patient thread through everything we do out here. The cosmos is vast, our tools are young but clever, and we learn to trade brute force for endurance, borrowing speed from gravity, listening to clocks, trusting the quiet geometry of orbits. The numbers look cool on a page, yet the work is warm in human hands. Someone, up before dawn, checks a trajectory. Someone else leans close to hear an engine's whisper. Another waits the long hours for a faint reply. When haste is wise, we make it. When slowness is kinder, we keep to it. And that steady rhythm often leads us to the quiet places, the ones that look still from far away, but are busy just beneath the surface. One of those quiet places is Europa, a small moon across Jupiter's wide court that hides its story under ice. From a distance, it's a pale bead traced with soft lines. Underneath, tides knead the world like slow hands and keep an ocean from freezing solid, maybe more water than all Earth's seas combined. Water lets chemistry move, and moving chemistry can learn to copy itself. Given time, copying becomes life. The distance does not care about our hope. Even when Jupiter leans closest, it waits hundreds of millions of miles away, and a craft that departs mid-decade may not truly begin its work until the middle of the next. So we breathe at that scale. We listen, we plan, and we keep the same patient beat we've practiced at home. A visitor bound for Europa must first ask permission from Jupiter. No one truly lands there in a hurry. The space around that giant is drenched in radiation. Machines must arrive with armor that adds mass, and mass asks for more fuel, and more fuel asks for stronger engines, and stronger engines ask for more mass again. The gentle spiral of difficulty reminds us that, for now, we choose to circle the system rather than plant our feet right away. Close flybys turn Europa from a dot into a world. Each pass lets instruments taste the thin air above the ice and listen for plumes that break through like sighs. It is the first chapter of a very long letter. We are writing with a slow pen so the page does not tear. If one day a whisper rises from that ocean and says that life is there, the next steps become even slower. A lander would need to find a safe plane. It would need to drill through ice as thick as mountains are tall. It would need to send a swimmer to the ink-dark water and guide it by touch alone. The road from a decision to a sample in a tiny vial would be measured in decades. The scientists who write the first lines of the idea might not be the ones who read the last lines of the results, Students who join the project in their 20s might be middle-aged when the first camera blinks under the ice. This is not punishment. It is simply what happens when goals stay large and the universe stays honest. Even when we are not moving a machine, we must tame the distance with time. Information cannot outrun light. The radio that links us to a rover or a probe flies at the fastest the universe allows, and yet the delay grows. As the miles stack up between Earth and Mars, the gap shifts with the planets. Sometimes a message makes the one-way trip in about 3 minutes. Sometimes it needs 7 times more. Control is not a joystick. It is a choreography written in advance. When a rover lands, it carries a sequence of steps that must unfold whether we watch or not. Humans on the ground hold their breath. By the time the news that a landing has started arrives, the dust has already settled. The result is already old. Relief comes with a timestamp that feels like a delayed heartbeat. Push this idea farther, and the delay becomes a slow tide. A craft near Jupiter answers after nearly an hour. A craft beyond Saturn waits longer. A craft like the ones that turned back to photograph Pluto sends a postcard that needs many hours to cross the dark. Real time becomes a story we tell ourselves for comfort. In practice, the machines must be able to think a little for themselves. They follow rules written by people who imagine what might go wrong and what might go right. They choose safe modes when signs look strange. They save data for later when the line of sight slips behind a planet. We give them autonomy not because we prefer it, but because distance requires it. Speed is a kind of energy poetry, and the stanzas are large. To lift a heavy craft a few hundred miles above the air is to spend the equivalent of harvests and dinners and the lights of cities. That energy is not waste. It is a doorway fee to a place where drag fades and orbits become quiet roads. The first step, low Earth orbit, still belongs to Earth's pull. Climbing free enough to visit another world asks for more than power. It asks for careful timing and for a willingness to accept that most of the mass that leaves the ground is fuel that will be gone by the time the crew sees the blue globe shrink behind them. Think of a simple target like the moon and how large a machine had to be to reach it. The tall white tower that thundered from Florida was mostly propellant. It held oceans of liquid oxygen and liquid hydrogen, and it spent them in minutes to trade weight for speed. That push was enough to arch a path toward the moon. For anything beyond, the exchange becomes sharper. The energy needed rises like a wall that tilts steeper the faster you want to go. Our math wrote this law long ago. It is a soft line on a page and a hard truth in metal and fire. If you want to double how quickly your path changes, you usually need much more than double the propellant. The curve does not forgive impatience. Imagine aiming for even a kind fraction of light's pace. 1/100th is huge by our standards. At that speed, the distance between continents shrinks to breaths, and yet the energy stored in the motion of a modest mass becomes the kind of number that belongs to superlatives. A 1-ton craft at such a pace carries the punch of weapons we keep locked behind history's gravest doors. Add life support, shielding, and space to live, and the mass grows by orders. Each order drags behind it more fuel, more structure, more cost. The numbers stop feeling like numbers and start feeling like myths. That is not to say it cannot be done forever. It is to say that with the tools in our hands now, a careful mind chooses nearer shores. The math that governs rockets has a quiet beauty. It asks us to think in ratios, initial mass to final mass, the speed of the exhaust to the speed we hope to gain. The natural logarithm sits at the center like a slow bell. It rings to remind us that every pound of propellant we carry must itself be pushed. The deeper the change we want, the more our starting ship becomes a tank with a small brain on top. This is why we search for engines with higher exhaust speeds, for designs that sip rather than gulp. This is why we borrow gravity from planets, why we plan paths that unwind like thread rather than stab like arrows. Sometimes the difference between speed and exploration hides in plain sight. There is a house that circles our planet every 90 minutes. The people inside see dawn and sunset many times in a single day. They float at 17,000 miles per hour, and yet they travel nowhere at all. Orbit is falling around the world without hitting it, a dance that keeps you close even when you feel fast. The same goes for a telescope that rides a similar path. It does not need to go anywhere. It needs to hold still with enough steadiness to catch ancient light. One philosophy says, move your eyes rather than your feet. It is a kind philosophy when the targets are too far for any vehicle we can build. We can read the sky from our backyard if we build our instruments with patience and keep them cold and calm. Another eye sits 1,000,000 miles out on a saddle of balance where the gravity of Earth and the sun shape a pocket of stability. The journey there is serene. The craft coasts for weeks at speeds that would make a fighter pilot yawn, and then it begins a long, slow loop around a point that is itself always moving. From there it listens in infrared, a color of heat that near Earth is drowned by our own warm glow. It sees galaxies that formed when the universe was young and thin. It tastes the breaths of planets that circle distant suns. It proves that looking well can sometimes outrun going fast. A still place can be a telescope's version of speed. Yet not every question yields to light alone. There are puzzles that do not spill their answers unless you show up with a hand lens and a drill. Whether microbial life hides in a salty pocket under Martian frost, whether Europa's ocean carries the chemistry that learns how to harvest energy and conserve its gains, whether the rocks of Venus hold a diary of watery youth or of volcanic storms that never rested. These cannot be settled from far away with perfect certainty. Someone or something must go, must touch and measure and compare. The clocks of careers and budgets and generations begin to tap their quiet rhythm. It is one thing to build a window and learn across the light years. It is another to put a laboratory on another world and be patient enough to wait for its results. When travel is the goal, designers become poets of compromise. They draw paths that are not straight lines, because straight lines burn too much. They choose a loop past a bright inner world to take a little of its speed. They accept journeys that take years, because those years save fuel that would have been spent to arrive early, only to be shed again in order to stop. They pick launch days with a care that feels like respect. A missed week can mean a lost year. A missed minute in a rare window can mean that a mission never recovers its elegant arc and must settle for a slower, heavier life. Close to the sun, even an easy target can be hard to hold. Mercury seems simple. It is small and near. Yet it sits deep in the stars' well, and anything that dives to meet it picks up fierce speed. To break at the end would ask for more than a reasonable tank can hold. So missions skate past Earth and Venus and even Mercury itself several times, each pass shaving a little of the speed until at last the craft can settle into a safe, slow orbit. The path looks like a scribble on a page. In truth, it is a patient staircase that trades time for fuel. As the map expands beyond our local family, the bright stepping stones thin out. Between stars, there are no handy giants to lean on. there is no breeze to catch. A ship that leaves the sun's influence must carry everything it will ever need, or learn to gather it from dust so thin it is almost not there. The trip ceases to be a human project and becomes a civilization project. Time deepens until it touches the word forever. We can imagine swarms of tiny machines that travel like seeds on a light beam and report back long after the people who sent them are gone. We can imagine arcs that hold communities who live and love and age among gardens under lamps that mimic the Sunday. We can imagine both and still feel the gravity of questions that are not technical. People are not cargo. They are stories with bodies. A crew on a station or on a voyage to Mars counts the days until they can feel weight on their feet again. They train their minds to find meaning in repetition and teamwork. They grow small rituals to tie themselves to Earth. A journey that lasts a few years is already a braided rope of resilience, medicine, humor, and good sleep. Now stretch that rope until it must hold for centuries. The rope begins to look like a chain. Children are born who never see a sky except the one painted on an inner dome. Elders die who never felt rain. The mission's original promise becomes a legend told at a table. The heirs might keep faith, or they might write a new faith. They might care for the hull like a cathedral, or they might wish to turn around and go nowhere at all. There is a way to dodge some of the weight of such questions by sending potential rather than people. Frozen seeds, embryos, recipes for life encoded in careful patterns, machines to teach and to raise. But then a different set of questions gathers around the cradle. Who becomes the first parent? What language names the first dawn? What culture the first song? If an intelligence grows from a library and from the guidance of a patient system, is the result ours in any honest way? The impulse to explore becomes tangled with the impulse to create. The lines blur. Some will say this is not exploration, but colonizing with shadows. Others will say that seeds do what seeds do. Even without crews, speeds and distances ask for a long view. Imagine a fleet of gram-scale craft that leave on a burst of light, their tiny sails pushed by a focused beam. 20 years later, a handful pass a nearby star at a fierce clip and begin sending back brief, precious bits. Those bits take more than 4 years to cross the distance. The people who built the array are older now. Some are gone. New hands tend the receivers. The images arrive like snowflakes. A planet seen as a few pixels. A spectrum that hints at weather and color. To some, this will be a triumph. To others, a sweet ache. It is both. Our speed limits turn out to be mirrors that reflect our limits of patience and care. They invite us to value the places we can reach and to build instruments that pull far worlds close without moving our feet. They invite us to teach machines to make good choices when alone and to write software as kindly as we write lullabies. They invite us to think about energy not as a number but as a culture. What are we willing to spend? What are we willing to wait for? What risks do we call acceptable on behalf of those who never chose them? On the good days, these limits deepen our sense of home rather than shrinking our reach. A telescope that listens from a quiet point in space can tell us about the weather of a planet we may never visit. A probe that tastes the brine of a moon can let our minds swim in that darkness without placing a human body in harm's way. A rover on Mars can grind a small stone and heat it to learn its story, while a person on Earth listens to the faint clack of the instrument and feels a small, warm pride. The entire planet becomes the crew. The night becomes the shared cabin. Missions keep us honest about how brittle speed can be. If you rush to arrive, you must pay to slow down. If you accept the long voyage, you might save enough to work once there. Each choice answers a different kind of desire. The desire to see now, the desire to learn well. Wisdom grows in the balance between the two. In that balance, a path opens that looks less like conquest and more like conversation. We ask a world to share a sample. We wait. We ask again with better words. We wait again. The answers come like tides. Look again at Europa in this light. A craft loops past and feels a tug in its orbit that betrays the depth of the ocean below. Another pass tastes faint, salty spray in the thin air. Another maps the thickness of ice by the way Jupiter's radio noise hums through it. Each piece is a thread. The braid becomes strong enough to pull a lander forward in our dreams. The lander someday listens for creaks, searches for places where ice looks young, where heat from below has softened the roof. Later still, a probe sleeps inside a drill and then wakes in black water and turns on a lamp the size of a coin. The light falls on flecks that drift. There is chemistry enough to brew. Whether there is memory there, or hunger, or a cycle that repeats, becomes the question that fills the room back on Earth, where people have kept faith for years. Speed still matters. It is the reason some questions answer in a single lifetime and others do not. But speed is not the only measure. Clarity is a measure. Safety is a measure. Continuity is a measure. A camera that sees farther than before turns time into a telescope. A mission that takes 10 years gathers thousands of hands and minds and teaches them to think together. Those who retire pass along the logic of the work, and those who begin find their place in a story already in motion. The sense of going somewhere becomes a way of being together. When the night is quiet enough, the limits feel less like bars and more like rails. They keep us from slipping into fantasies that burn out. They allow us to aim for near goals with tenderness and for far goals with honest eyes. There is room for all of it, for the slow parade of flybys that paints a moon with detail, for the ambitious concept that sends a dust mote across the void like a brave spark, for the people who choose to stay on the ground and make the instruments better, for the brief, bright launches that lift our hearts, and for the long, soft waits that deepen our patience. We are a species that builds ladders out of ideas. The rungs are transit times, and launch windows, and signal delays, and energy budgets. The hands that climb hold clipboards and wrenches and coffee and sometimes a child's drawing taped to a monitor. The view from each rung is a little wider. The air is the same. It smells like metal and dust and someone's lunch. The ladder goes up the side of an old dream. It is not glamorous most days. It is stubborn. It is kind. It moves at the speed of trust. So the search for life beyond Earth is not a race. It is a listening. It is a careful walking. It is a promise made to strangers who are really our future selves. We promise to carry the question forward even if we do not carry the answer back. We promise to keep building tools that see clearly. We promise to think about the minds and bodies we send, and about the minds and bodies we ask to wait. We promise to let the scale of the universe make us gentle rather than small. The ocean under Europa is still dark tonight. The radio dishes on Earth still turn their white faces to the sky. Somewhere, a planner checks a trajectory and changes a number by a tenth and smiles. Somewhere, a student writes code that will decide how a probe should behave when a sensor sees something odd. Somewhere, a technician tightens a bolt and hums without knowing it. This is how far we travel right now. This is how fast. Not only in miles per hour, but in care per hour, in patience per hour, in wonder per hour. The limits teach the tempo. the tempo fits the heart. And in that steady beat, the long search becomes livable and even sweet. There's a kind of space weather that neither sparkles nor roars, yet it shapes every mile we hope to travel. Call it radiation. It has no color, no scent, and little mercy. Some pours from the sun in gusts. Some was born in stars that died long before cities. Some drifts like a faint wind through the thin gas between the stars. Near Earth, we live under a magnetic canopy that bends much of this rain away. Even so, astronauts in low orbit take several times the dose we receive on the ground. A steady drizzle, doctors count, and flight surgeons respect. It sets gentle limits on how long a person should work up there, but with smart shielding and careful schedules, it can be managed without drama. Step past that magnetic roof and the tone changes. Solar energetic particles arrive in sharp flurries after flares, sudden squalls on an otherwise quiet sea. Galactic cosmic rays, heavy atomic nuclei near light speed keep a slow, relentless beat that never stops. Spacesuits and aluminum walls help, but not enough by themselves. A voyage to Mars means months in transit, then months on a surface with a thin atmosphere and no global magnetic field. The dose accumulates day after day, pushing lifetime cancer risk upward in numbers you can point to. For a single expedition, planners can box that risk and still call it acceptable, but the margin is slim. Stretch the timeline to decades, and the arithmetic grows stern. On journeys longer than a career, that steady rain becomes the main plot. Water makes an excellent, gentle shield. Hydrogen-rich plastics help. Bricks of regolith or frozen panels can be stacked into walls. Designers bury bunks near a ship's center and wrap them with tanks and supplies, so necessity doubles as armor. They add a compact storm shelter where the walls are thickest for days when the sun lashes out. Every layer is weight. Weight demands thrust. Thrust demands fuel more weight. The rocket equation taps its rhythm on the table. To be safer, carry more. To go faster, carry more. To carry more, bring fuel to push the fuel you brought. There is no cheating the ledger, only choosing which column to grow. Speed adds an almost unfair complication. The interstellar medium is unbelievably thin, a ghost of hydrogen atoms spaced like lonely thoughts. At ordinary speeds, they're harmless. Raise your pace to 1/10 of light, and each atom hits the bow with the bite of a cosmic ray, spawning showers of secondaries that sprint through metal and tissue. Push toward a few tenths, and the fog ahead behaves like the edge of a reactor core. The faster you go, the harder the rain falls. The harder the rain falls, the more armor you carry. The more armor you carry, the more energy you need just to keep moving. Soon the circle tightens until it feels less like a plan and more like a warning. Engineers sketch umbrellas against this invisible weather. One idea wraps a ship in a magnetic cocoon, a miniature magnetosphere that nudges charged particles aside. Another adds electrostatic plates to steer ions away before they bite. The physics cooperates on paper. In practice, those fields must be strong, stable, and wide compared with the hull. That asks for compact, high-power sources, radiators to spill waste heat, cryogenics if superconductors keep coils cool, controllers that never sleep. Each subsystem brings mass, heat, and complexity. The umbrella works only if the hand that holds it can lift it for years without rest. Navigation changes its voice as speed climbs. On a road, a wrong turn is a flick of the wrist. In deep space, a wrong turn is a change in velocity, and every change costs propellant. At 1/10 of light, even a 1-degree trim is a major event. The course you draw at launch must account for the target star's proper motion, the sway of its planets, the sun's slow walk around the galaxy, and tiny pushes from interstellar gas. Star trackers and gyros must be brutally honest. Clocks must keep faith for decades. You aim not where a star is tonight, but where it will be when your messenger arrives. By the time an error is obvious, you may be millions of miles off, and the burn to fix it could cost more propellant than any ship could carry. Go faster still and dust grows teeth. Interstellar space holds grains of silicate and carbon, flecks of ice, tiny scraps from old comets. They're rare, but a path measured in light years turns rare into likely. A speck smaller than sand, striking the bow at 1/5 light speed, carries the punch of a grenade. A pebble is a bomb. Designers talk about sacrificial shields, meters of ice or water that flash to vapor on impact, carrying away energy before it reaches the heart of the craft. They imagine thin foils stretched far ahead, so the first touch of dust becomes a faint plasma cloud that spreads and softens the blow. Magnetic curtains might sweep charged grit aside, but neutral rocks keep their stubbornness. The higher the speed, the sharper the minefield feels. Beneath all this runs another current, the price of ambition. Big projects on our doorstep already ask a lot of the societies that fund them. A lunar program employs hundreds of thousands and budgets of small countries. A long-lived outpost in low Earth orbit costs oceans of money and patience. A great space telescope demands decades of argument, repair, and craft before its first image brings tears to a control room. None of this is waste. All of it builds tools, talent, and trust. Yet, at the edge of an interstellar proposal, the columns stretch past the page. The costs sprawl across elections, careers, and cultures. Supporting a mission that will not sing back for half a century or more requires a new kind of will, almost a technology of its own. One answer imagines an economy spread beyond Earth's well. Mines in the asteroid belt feed foundries in orbit. Solar power stations beam energy where it's needed. Factories in microgravity build mirrors wider than cities and trusses light as silk. In such a future, a star probe might be a cathedral effort, hard but not absurd, funded by a culture that thinks of itself as spacefaring by default. Even then, choices remain. Expand gardens on the moon and habitats in cislunar space, or pour treasure into a ship that will send a radio postcard from another sun long after its architects are gone? The choice is not only technical, it's ethical and cultural. It asks who we are trying to be for people we will never meet. Meanwhile, imagination lays engines on the bench. Antimatter rockets shine brightest in theory. Matter and antimatter turn nearly all mass into energy. Direct that into a jet, and you have the highest ceiling equations allow. Reality is less romantic. Today we make antimatter in nanograms at prices that read like misprints. Storing it safely needs magnetic bottles in high vacuum, powered with a steadiness that leaves no room for a blink. A containment failure isn't a puddle under the ship, it's a bright, final flash. That doesn't mean never. It means much later, after long advances in production, storage, and control. Fusion rockets feel closer. The sun runs on fusion, so do a few hard chapters of our history. What we haven't built is a steady, compact reactor that gives more energy than it drinks and can ride inside a ship. If such a machine arrives, and if it can throw exhaust at a few percent of light speed, interstellar travel becomes stark and slow rather than impossible. Old studies favored deuterium mixed with helium-3. Helium-3 is rare on Earth. Sketches imagine skimming Jupiter's upper air for it, or baking it from lunar soil by the ton. Each line becomes an industry: tankers, refineries, depots, and the quiet logistics that keep them from falling silent. Another family of ideas keeps the ship light and moves the heavy work outside. You carry a sail, someone else carries the engine. Near the sun, a field of mirrors concentrates light into a beam that pushes a wafer-thin sail until it's racing. The craft rides a river of photons and leaves propellant at home. This saves enormous mass at launch, but asks for mirrors hundreds of kilometers across that live in fierce heat and radiation, for guidance that can hold a spot steady across millions of miles, and for safety systems ensuring nothing on Earth gets scorched by a misfire. Beams spread, sails drift. Sooner or later the push fades. The idea is beautiful and honest about its limits. Some engineers would rather surf particles than light. A magnetic sail is a loop of superconducting wire that makes a magnetosphere bigger than the ship. Solar wind and the thin breeze of interstellar ions push on that bubble like a constant hand. The sail is geometry, not cloth. Superconductors want to be cold and clean. Space offers micrometeoroids, radiation, and the occasional hot breath of a flare. A quench can collapse the field in a heartbeat. The ring must be strong, repairable, and charged by a stout power source. It must also be very, very large. The Bussard ramjet is the bold cousin that won't leave the party. Set a magnetic scoop the size of a small planet ahead of your ship. Gather thin hydrogen between the stars. Compress until fusion lights, then throw plasma behind. You never run out of fuel because the road is your tank. The catch is density and drag. Interstellar gas is so sparse, the scoop must be enormous to collect much. And scooping can pull back harder than the thrust you gain until you're already very fast. There are tweaks, beamed fuel, or using the scoop as a magnetic brake on arrival, but the circularity holds. It's a door that opens only after you're inside the house. When the toolbox feels empty, minds wander to the fabric beneath it. General relativity says space-time bends and stretches with energy and mass. If you could compress space ahead of a ship and expand it behind, you could carry the ship along without anything inside breaking the light speed rule. The math for this warp metric holds together. The materials and energies it requires are not in our pantry. It asks for negative energy densities we glimpse only as tiny quantum effects, not bricks we can stack. It asks for control that feels like asking a blacksmith to build a computer. The dream isn't banned by physics. It's fenced off by distance from where we stand. Wormholes tempt for the same reason. Shortcuts that ignore distance. Equations allow tunnels with throats you could, in principle, fly through if you can hold them open. Holding them open seems to demand exotic matter with negative energy and stability conditions that read like wishful spells. Many solutions invite time loop paradoxes physics may forbid, with rules we don't yet know. Even if nature makes wormholes, they may be microscopic and snap shut the instant you try to push a photon through. The universe often permits beauty on paper that it keeps locked away in practice. While we wait for engines we don't have, we still travel and keep people and machines safe. Radiation becomes a design language. Put bunks at the center. Wrap them with water tanks and food lockers so necessity doubles as armor. Build a compact storm shelter where the walls are thickest for days when the sun spits. Use smart materials that self-heal microcracks so small wounds don't grow into failures. Teach a ship to think gently for itself. When the line to Earth is slow, point the nose away from a known hazard. Pause a science sequence during a storm. Save data for later. keep the crew in the quietest room. Aim becomes a ritual practiced with patience. There are no quick turns when inertia is measured in millions of miles per hour. You point the nose not where a star is, but where it will be. You fold in the target's motion, the tug of neighbors, the drift of gas, the heartbeat of your clocks. Launch windows are slices of time when those moving pieces line up just so. Miss the slice, and the story shifts by months or years. Precision at the beginning is mercy at the end. There's also a gentler strategy that treats patience as an engine. Learn more from here while learning how to go far. Build telescopes where heat is low and light is steady. Chill them until they can taste the breath of planets around other stars. Spread radio dishes and braid their signals to hear whispers from the edge of the galaxy. Tie instruments and archives so data becomes more than the sum of parts. This doesn't replace going. It buys insight, time, and sharper questions to carry when we do go. Limits, seen kindly, give back more than they take. They make us collaborative. A Mars mission braids engineers, physicians, biologists, coders, cooks, and counselors into a guild that keeps humans healthy far from home. A deep space telescope trains a generation in optics, cryogenics, vibration control, and the patience of calibration. Radiation studies for astronauts become better care for patients on Earth. The ship that doesn't exist yet leaves footprints in labs, classrooms, and hospitals. Hold Europa in mind to see this in practice. A spacecraft loops past and measures a delicate wobble that reveals the depth of the ocean under ice. Another pass tastes salty vapor that bubbled up through a crack and froze into snow. Another maps ice thickness by timing how radio from Jupiter threads through it. Thread by thread, the case strengthens. The day for a lander comes not because we sprinted, but because we kept rhythm long enough to be sure. A drill bites, a probe wakes in black water, and a coin-sized lamp paints drifting flecks in a cone of light. Chemistry is lively here, even if biology is not. The news comes home as a faint song across 1 billion miles. The people who pushed for that song breathe and smile. The ones who inherit the work open their notebooks and ask the next gentle question. Speed still matters. It decides whether a question answers within one lifetime or across several. But it isn't the only measure that counts. Clarity counts. Safety counts. Continuity counts. A camera that sees deeper turns time into a lens. A mission that endures turns a workforce into a memory you can hand down. The line between going fast and going well is not a border to guard. It's a garden where both can grow if tended with care. Somewhere tonight, a team checks a simulation of how cosmic rays thread a layered hull. Somewhere else, a technician tapes an extra strip of water ice to the nose of a test article and listens for the pop when a dust gun fires. In a quiet office, a navigator redraws a trajectory and smiles. Saving 100 meters per second of delta V feels like finding grain at the bottom of a barrel. Under a corrugated roof far from the city, someone looks up and is comforted by the same points of light that once taught sailors to cross oceans. The ship we dream about is still a sketch. The skills we need are already in motion. The universe is not our enemy. It is a strict teacher with clear rules. Radiation is one lesson, dust is another. Budgets, politics, and ethics are the rest. When we hear the lesson and answer at a human pace, the classroom becomes a workshop, and the workshop starts to feel like home. In that steady mood, speed becomes less a dare and more an invitation. It invites better shields and medicine. It invites deeper instruments and quieter software. It invites braver yet kinder visions of how many generations can hold a promise without dropping it. Maybe the first star messengers will be chips on sails, tiny and brave, riding a river of light. Maybe the first human footprints beyond the inner system will be on moons made gentle by domes and caves. Maybe the first true interstellar travelers won't be people at all, but libraries that teach new people how to be human when they arrive. Every path has its price and grace. The important thing is to keep the conversation going, not only with the sky, but with each other. So we keep building. We count the rads and the grams and the dollars. We count the minutes of a launch window and the milliseconds of a star tracker. We count the generations of a mission that must outlive its founders. With each count, we add a little more patience to the stack. Engines will come. Shields will grow lighter. Sails will stretch wider. Fields will hum steadier. When they do, we'll still need the soft skills speed can't buy, the habit of care, the craft of aiming well, the courage to accept delay without losing the thread, and the grace to place the thread into the next pair of hands. Space does not rush. It is old and wide and calm. If we match that mood, our work becomes a kind of rest. We can go slowly and arrive ready. We can learn from here while reaching for very hard things. The night is quiet enough to hold this hope. The instruments whisper, the teams breathe, the dream stays warm. Let's bring the horizon a little closer and ask what steady hands might build within the next 50 or 100 years. The tools are not magical. They are familiar, patient, and ready to be refined. Nuclear thermal engines heat a light propellant with a compact reactor and push it out the back at twice the exhaust speed of chemical rockets. Nuclear electric systems feed that same reactor's power to ion thrusters, trading fireworks for a blue whisper that never gets tired. The physics is kind, the engineering is in reach. What wobbles is will and wallet. With these engines, a trip to Mars could shrink from a long pregnancy of 9 months to a season or two. Cargo would arrive fresher. Crews would spend less time bathing in radiation between worlds. Outer planet missions could grow heavier and braver, carrying laboratories instead of briefcases, orbiters that linger instead of flybys that wave. Unlike chemical stages that burn hard for minutes and then coast forever, ion drives can keep their gentle hand on the shoulder for years. A ship that accepts the slow push can spiral outward, touch a target world, and then spool up again toward a second destination without asking for a giant new tank. The Dawn spacecraft gave a small preview of this life: arriving, working, leaving, arriving again. Expand that idea with a reactor instead of solar panels, and you get a platform that can wander the system with deliberation. Main belt, Jupiter, Trojans, Saturn's families, Centaurs, into the Kuiper belt, taking its time, the way a good field scientist does, setting up camp where the rocks look interesting and the light is kind. Farther out, where sunlight thins, nuclear electric makes sense. Nearer the sun, sails can do quiet miracles. A polished film no thicker than a whisper can catch photons and turn the pressure of light into motion. It is gentle acceleration, but gentleness is not the insult it sounds like. When there is no air to slow you, tiny pushes add up. For missions that are not in a hurry, mapping the solar wind, listening for dust, hopping between small bodies, a sail is a thrift engine. And for ambitions larger than thrift, you can imagine constellations of small sailcraft, each no bigger than a tray, fanning outward on different bearings. They do not need propellant or tank farms. They launch cheaply, many at a time, like seeds. A few will fail. A few will phone home with nothing special to say. A few will drift into corridors of surprise and send back data that changes textbooks. Multiplied over decades, that slow hail of postcards could sketch the outskirts of our neighborhood with a fidelity we have never known. There are also windows that open when materials improve, better reflectors, lighter booms, films that heal after micrometeor hits, higher temperature reactor cores, long-life pumps and bearings, high-voltage power processing that sips waste instead of spilling it as heat, radiation-hard computers that run for decades without a babysitter. These are not headlines. They are the quiet bones of a century of exploration. Each improvement trims a pound, saves a watt, stretches a schedule, the savings compound. Somewhere between the near and the romantic sits the idea of nuclear pulse or fusion pulsecraft, vehicles that do not burn continuously but take repeated, powerful steps. The concepts are old, the math is not offended, and the breaks, political, environmental, and practical, are not imaginary. If those breaks someday loosen under rules that value sterility and distance, the result could be probes that manage 1% or 2% of light speed, perhaps 5% in brave scenarios, especially if they are small, unmanned, and built to accept accelerations that would be cruel to a human body. A fleet of such messengers, launched over decades toward a handful of nearby stars, would turn centuries into timescales we can at least talk about. It is tempting, always, to ask for a miracle. Physics has surprised us before. Quantum rules turned the small world inside out. Relativity turned speed and gravity into geometry. Dark matter and dark energy are signs on the highway that most of the universe is written in a dialect we cannot yet read. It is wise to leave a crack in the door for the unknown breeze, but it is also wise not to lean your life on it. Planning must flow from what we can build, while keeping a clean shelf where revolutions, should they arrive, can sit down comfortably. For the next century, the likely speed limit for machines that carry their own brains is a few % of light, and then only for small, tough craft that do not mind being lonely. For people, with their water and air and songs and laughter, the limit will be lower. That is not failure. That is simply the size of the room we are in. The goals shape the engines. Robots tolerate vibration, temperature, and acceleration that would injure a living crew. They do not need gardens, doctors, or windows. They do not get bored. They do not dream of home, and they do not panic when the sky outside is a perfect, unchanging black. A machine built for 1,000 years has to be patient and self-repairing, but it does not ask for Sunday dinners. A ship meant for families is another universe. Layers of shielding, rooms where children can run, water recycled into water again, light that changes on purpose so time feels real. Counselors and storytellers, and farms in rings that pretend to be gravity. That kind of arc is not a spacecraft in the way we use the word today. It is a town that happens to move. The engineering is loving and enormous, and beyond any single generation's shoulders. Because of this, machines will go first almost everywhere. They will scout, taste, and decide where humans might safely stand. If they find something that sings to us an ocean worth diving, a chemistry that begs for company, a landscape that makes the heart beat faster, then people will follow carefully, with an honest appreciation for what it costs to keep a heartbeat warm, far from the Sunday. That path is not cowardice, it is craft. Robots open doors. Humans choose which rooms deserve a long hello. Consider a very specific door, Proxima Centauri. From Earth, we can already learn a surprising amount. We know the star is a red dwarf with moods. We have traced the small tug that reveals a planet in the temperate zone. We read atmospheres with spectroscopy, breaking starlight into colors and searching for patterns that whisper water or methane or oxygen out of equilibrium. Telescopes that sit cold, far from Earth's glow, sharpen this reading year by year. What could a probe in that system add? Almost everything that makes a place real. Weather that changes in an afternoon, clouds that pile on mountain ranges, the texture of dust, the way light breaks in a wave, the soundlessness of a sunrise from a surface with 1/3 of Earth's gravity, the exact thickness of a sky, how a magnetosphere, if there is one, wraps the planet in aurora. From nearby, we could pluck a grain from a ring, taste an ocean plume if there is ice and tide, and bring the discipline of geology to bear on a world that has only been a smear in a data set. There is a puzzle, though, that every planner whispers about: the weight calculation. Send a slow messenger now, or wait for a faster messenger later that might pass the first on the road and arrive earlier. Technology does not always march in a straight line, but it often enough does that the puzzle bites. Wait long enough and you may always be waiting, like someone who refuses to plant a tree because a better shovel might go on sale next spring. Commit too early, and you risk a century-long mission that delivers less than a telescope your grandchildren could build from orbit around Mars. There is no formula that answers this cleanly. At some point, courage and clarity shake hands and accept the possibility of being overtaken. Progress likes to see boots on the road. The Voyagers were not perfect, they were present. Because of that, half a century is now filled with measurements that would otherwise be blank. If you tally the speeds we can make now and the ones we can plausibly make soon, a pattern appears. Launches sprint at thousands of miles per hour, then coast. Planetary transfers sit in the tens of thousands. With long-burn electric or nuclear electric, a craft can walk its way to hundreds of thousands and sometimes into the low millions with enough time. Add beamed pushes or pulse concepts, and a small, brave probe might flirt with a few percent of light. Humans will ride at the low end of that spectrum for a long time, not because we are timid, but because we are tender and worth protecting. These numbers are not fit for conquering the galaxy by lunch. They are perfect for filling our own house with detail and for sending scouts to the nearest fence posts in the night. Inside those numbers lives a more interesting truth. The purpose of a trip changes what fast enough means. A mission to map Mars's deep water and practice landing heavy cargo wants shorter transit to spare crews radiation and to trim launch mass. A mission to tour the outer planets wants endurance more than haste. The sceneries are not going anywhere, and orbits are a patient business. A mission to sniff the Kuiper Belt cares about power and reliability and detectors that stay honest in the cold. A starshot cares about the first 2 hours and the last 2 minutes, when aiming and braking, if braking is even possible, decide whether centuries of flight end in a blur or a sentence worth reading twice. And then there is the matter of time as a teacher and a test. Projects that last decades become cultures. They gather apprentices and elders. They survive elections and fashions. They learn to hand the baton across retirements and birthdays. The International Space Station is a quiet proof of this patience. Modules from different nations, bolted together over many years, kept alive by people who were children when the first drawings were made. An interstellar attempt, even an unmanned one, would demand an even sturdier culture, asset management that laughs at a fiscal year, archives that do not rot, and a habit of kindness between teams who will never meet except in footnotes. If this sounds slow, it is. Slow is not a flaw. Slow is the pace of gardens and granite, and grandmothers who teach a child to read. Spacework at today's speeds asks us to be that kind of species often, the kind that plants without needing to see the harvest. The reward is not only in a distant postcard, but in the craft that forms at home while we wait. New detectors built for dark, cold space find tumors earlier in hospitals. New alloys spun for cryogenic plumbing become lighter bicycles and stronger bridges. New algorithms that keep a probe sane during a communications blackout keep an airplane honest when sensors disagree. The dividend of patience is broad, and there is beauty in this middle speed. By biology's measure, we are already outrageous. Nerve impulses zip at highway pace. Falcons dive like thrown knives. Cars and trains and jets leave those numbers embarrassed. We keep pushing. We have pushed so far that a person can circle the earth in the time it takes to watch a movie. We are also, against the yardstick of light, comically slow. That odd in-between is not a humiliation. It is context. We are clever animals in a very big room. We have learned to draw maps of the ceiling while still living close to the floor. We can savor both truths at once. Pride that our reach is now measured in planets. Humility that our neighborhood is only a bright porch light on a long street. So the next 50 to 100 years look less like a race and more like a long walk done well. Reactors that hum without fuss. Ion engines that earn trust over decades. Sails that unfold cleanly and keep their shine. Navigation that treats aim as a ritual. Ship software that chooses caution without drama when storms hiss on the radio. Crews who cross interplanetary space in months rather than most of a year and land with strength left for real work. Robots that make the outer system feel local with patient orbits and careful sampling. Scouts that leave the sun's garden without the promise of ever coming home. Small and brave and good at sending letters. We do not need to pretend this is enough to silence every ache. There will still be nights when the stars look close enough to touch, and it hurts a little that they are not. There will be press conferences where someone asks when people will walk on a shore that circles another sun, and the honest answer will still be a soft, not yet. But not yet is not never. Not yet is an invitation to become the kind of civilization that can carry a promise for a very long time without letting it spoil. If we do that, if we fly steadily, build carefully, share widely, and teach the habit of patient courage, then the limits of this century will feel less like walls and more like railings. And railings are useful. They let you lean out over the dark and look safely for as long as you like. A million years from now is a phrase that feels too large for the tongue, and yet it is a useful lantern. Imagine descendants, ours, or some mindful heirs looking back at this era the way we look at canoe cuts in Riverstone. They might cross the galaxy with the ease we cross a bay, folding space with tools we cannot name. Or they might learn the same lesson we are learning now, that the fabric of the universe asks for patience, that distance is not an enemy, but a scale that tunes the song. Either way, this moment will be the opening bars. Right now, we are the hands at the rail, sending machines to other worlds, setting telescopes in cold shadows, training crews to live where Earth is only a star. Our speeds are humble, but our direction is steady, and that is worth a quiet celebration. Consider the two small elders we sent first. Voyager 1 and Voyager 2 have slipped beyond the sun's strong breath into the thin country between the stars. Each carries a golden record, a patient capsule of music and greetings and images, a baby's cry, a heartbeat, waves on rock, hellos in dozens of languages, a kiss of Bach and blues. Those plates may outlast our cities and perhaps our species, turning slowly in a darkness that does not age. The craft themselves fly at a humanly astonishing pace and a cosmically slow drift. Tens of thousands of years from now, they will only be approaching the neighborhoods of other suns, yet their journey is still profound. They are bottles set adrift, not to demand a reply, but to leave a trace. We were here. We reached. We tried to touch the stars, even knowing our fingers were short. That, more than any record speed, is the center of our work. To explore at today's pace is to plant an orchard whose fruit our great-grandchildren will taste. It is to launch a mission, knowing the final paper may carry the names of students not yet born. It is to ask questions without a guarantee of answers inside a fiscal year or a career. The courage here is quiet. It looks like patience meeting after meeting, years of testing, one more redesign for a gasket or a hinge. It looks like resilience when a valve sticks, a spectrometer blinks, or a launch slips, and the whole team breathes, fixes, and tries again. Speed still shows teeth in our time. The Parker Solar Probe has learned to dance where sunlight is fierce. It loops around Venus, trades momentum, and dives within a few million miles of the star, skimming the corona, tasting magnetic swirls and dust that flows like wind. At closest approach, it flies more than 400,000 miles per hour, numbers that feel like fiction at a kitchen table. That pace would carry you from New York to London in a single breath. And yet, when set against the gulf to the nearest star, the number is a whisper. The contrast does not diminish the achievement, it sharpens it. Every heat shield that survives a near-sun pass remakes materials science. Every gravity assist, polished by practice, remakes our craft with orbits. Every line of software that steers autonomously in a storm remakes our understanding of how machines can share judgment. There is a practical chorus that deserves a fair hearing. We have needs at home. The answer is not to shrug, it is to notice proportion and return. Space budgets are small braids in the great river of public spending, and yet the braid ties many shores together. Weather forecasts, crop planning, search and rescue, ship routing, airplane safety, disaster response, climate monitoring, all lean on satellites. So do ambulance routes and delivery trucks and farmers' irrigation schedules, guided by timing signals that come from clocks floating high above. Medical imaging borrows tricks from instruments meant to read the cosmos. Water purification, solar cells, insulation, batteries, radiation therapy, wildfire mapping, threads from spacework run through them all. Curiosity alone would be reason enough, but the side gifts are everywhere. Another reason wears a heavier face. A species in one cradle is a species at risk. Asteroids do not read calendars. Volcanoes do not take polls. Pandemics and wars require no invitation. To make homes on the moon or Mars is not to abandon Earth. It is to accept responsibility for keeping culture alive through bad weather. Even slow travel is better than unrooted hope. A small, steady presence beyond Earth becomes a second library branch. If a fire takes one building, the story survives. Insurance is not romance, it is care. What keeps the fire warm in the meantime is the search for company. Are we alone? Sounds simple and lives deep. We can answer it piece by piece, patiently. There are worlds close enough for instruments to touch. Mars, where frost keeps secrets. Europa and Enceladus, where salt water hides and sometimes sprays into space. Titan, where lakes of methane lie. under an orange sky. There are planets far away whose atmospheres we can read by splitting starlight into colors and looking for patterns that whisper water, methane, oxygen out of balance. Our speeds limit our reach, but not our eyes. We can listen from here and learn, and we can still travel to the nearby places that matter most for the first answers. Persistence is, perhaps, our strongest engine. The Opportunity rover was offered 90 days and stayed 15 years, strolling until a global dust storm asked it to sleep. Hubble has watched the sky for more than 3 decades, measuring the births and deaths of stars and tuning our sense of cosmic tempo. The Voyager's whisper still, nearly half a century on. Endurance turns slow motion into a different kind of speed, the speed of accumulation. Grain by grain, photo by photo, spectrum by spectrum. Knowledge piles up until what was once a blur becomes a face with features you can name. A long view also changes how we judge fast enough. In daily life, faster often means better. In exploration, faster is one instrument in a larger orchestra. Accuracy and reliability are the strings. Efficiency is the woodwind. Slowness, time to linger, to circle, to return, is the percussion that keeps the rhythm honest. A swift flyby gets a postcard and a headline. An orbiter that stays gets seasons and storms, migrations of dust, the sigh of geysers, the slow settling of rings. Dawn's ion engines let it court Vesta, and then Ceres in turn, doing the kind of long listening that changes a hunch into a history. Cassini's patient years at Saturn revealed an ocean beneath Enceladus and rivers of methane on Titan. No sprint would have found those stories. Speed is how you arrive. Time is how you understand. There is also a softer freight to carry, and it matters. The pictures we make, the pale blue dot draped in atmosphere, the pillars of gas where stars are born, the rim of a crater in Martian dawn change the angle of our mirror. Borders vanish. Corals look small from 200 miles up. Children in city apartments and Rust Belt towns and desert villages point at the same crescent moon and feel the same tug. That feeling will not feed a family on its own, but it has a way of opening the hand that later learns to build, to vote, to share. Perspective is not a luxury, it is a quiet tool. Still, attention never fully goes away. Launch now or wait. A mission sent today might be passed by a faster one launched 30 years from now. A mission delayed forever will never write a first line. The cure is not a formula, it is a habit. Decide with clear eyes. Choose aims that remain valuable, even if technology outruns them. Build architectures that can be upgraded while they travel, software that learns, instruments with modes we do not need yet but will, ports where new payloads can dock. Accept that being overtaken is not failure if what you sent still teaches. The Voyagers were not perfect, they were present. Because of that, whole chapters exist that would otherwise be blank. So what, then, of speed itself numbers to hold in the hand? For now, our fastest messengers driven by gravity and the sun's well can taste 400,000 miles an hour for brief, brilliant moments. Crude capsules leaving Earth's care have reached roughly 25,000 miles an hour on their way to the moon. Ion engines keep ships in the tens of thousands for years and turn that steady push into great arcs. With technologies we understand, but have not yet built at scale, nuclear pulse steps, compact fusion, beamed sails, small, hardy probes might one day manage 1% or 2% of light speed. perhaps a little more. People, with their water and air and songs, will ride the lower end of that spectrum for a long while, not because we are timid, but because we are tender and worth protecting. If those scouts arrive to find that our telescopes at home have already learned many of the same facts, the journey will not be wasted. Up close is different. Up close hears the wind. Up close counts pebbles and watches clouds grow and die in an hour. Up close lands and finds the surprise no spectrum can preview, an odd mineral in a crack, the way dust holds a footprint, the discoloration around a vent. Science is not only an answer, it is the texture of an answer. A visitor can read that texture in ways even the finest distant eye cannot. In all this talk of engines and aims, there is a simpler reason we keep moving. We are not satisfied with a single horizon. We cut trails in mountains and stand on shorelines and wonder what is beyond the next line of foam. When our tools were canoes, we made maps with stars. When our tools were radio dishes, we made maps with whispers. The scale has changed. The impulse has not. At its best, it is not greed or conquest. It is the wish to meet the world where it is and to learn its names. So we will keep to this careful pace, reactors that hum and forget themselves, sails that unfold cleanly and shrug off the small punctures of dust, software that prefers safety to heroics, navigation that treats aim as craft, not luck, crews that cross interplanetary gulfs in months rather than most of a year, land rested and work. Robots that make the shadowed edges of our system feel like neighborhoods, scouts that leave the sun's warmth without any promise of return, good at sending letters and better at surviving. Maybe 1,000,000 years from now, someone will open a drawer in a museum built under another sky and hold a golden record against a palm, smiling at the crackle of an old hello. Maybe they will marvel at how slow we were, and maybe they will envy how brave. Maybe they will see in our pace a kind of wisdom we sometimes forget to notice in ourselves, the choice to move without panic, to aim without arrogance, to try even when the ocean looks unswimmable. Whatever their judgment, we can leave them this: a chain of careful work, a tradition of long promises kept, and a habit of kindness toward the future. The universe has its rules. Light sets the speed limit. Energy must be paid in full. Mass resists hurry. These are not insults. They are the grammar of the place we live. Within that grammar, you can still write beautiful sentences. You can still make meaning. You can still send a small machine into the dark and let it become a speck of intention no larger than a dime, and nevertheless real. That is what we are doing now, in this slow, steady chapter. It is not a sprint. It is not a pause. It is a walk, and a walk can cross a continent if you keep your feet kind and your compass true. So keep the pace. Celebrate each careful mile. Make tools that last. Share what they see. Teach the next pair of hands where the switches are and where the soft spots in a plan like to hide. When the night is clear, step outside and find the point of light that is a planet you have now walked in your mind. Let the scale humble you without shrinking you. Then go back in and do the small work that moves a ship a little farther. This is how we travel at the speeds we have. This is how, one patient day at a time, we turn slow into enough and enough into wonder. We can take a quiet step back and trace how our speed grew from a spark to a steady flame. The story is not a straight line. It is a patient staircase with shallow rises and landings for breath, a few leaps that thrill, and handrails called limits that our hands still feel every time we climb. In 1957, a metal sphere the size of a beach ball crossed the night. Sputnik 1 circled Earth at roughly 18,000 miles per hour, fast enough to fall forever and call that falling orbit. 4 years later, Yuri Gagarin rode the same band of speed, a single loop that made the planet both huge and suddenly holdable. Those first steps were not about getting far, they were about proving we could leave at all. The next move needed a different verb. To go from up to out, you must pass a number written into Earth's gravity, about 25,000 miles per hour. The Apollo missions lit stacks of fuel tall as cathedrals and rode that number cleanly. Translunar injection put crews on a 3-day arc at highway speeds for the soul, roughly 25,000 miles per hour, in the quiet between worlds. For the first time, humans were not just orbiting a home, they were changing homes, even if only for a handful of nights. The psychological shift was as large as the delta V. We weren't only going up anymore, we were going away. After such a crescendo, you might expect the tempo to keep rising. Instead, human speed took a gentler path. The space shuttle was built to reach low Earth orbit and work there, to carry laboratories, fix satellites, and help assemble a station where many flags could live together. Its maximum speed, about 17,500 miles per hour, was perfect for that job, and lower than Apollo's sprint. For 3 decades, crews lived fast enough to circle the planet, but not fast enough to leave it. Progress had not stalled. The goal had changed. We traded distance for presence, sprint for service, exploration for infrastructure. Uncrewed craft continued to test how quick a small machine could move. The twin Helios probes skimmed close to the Sun in the 1,970 seconds and briefly touched speeds above 150,000 miles per hour, trading proximity for pace. The Voyagers took a different route. They stole a little momentum from giant planets and turned those gifts into a lifelong glide outward, settling at tens of thousands of miles per hour with the grace of a stone thrown long ago that never lands. These were not records for their own sake. They were proofs that gravity assists, chosen with care, are the only honest way to buy speed in bulk without hauling oceans of propellant. Another leap did not come from fire but from patience. Ion propulsion turned electricity into a breath of thrust that hardly bends a feather, and yet, given years, changes a ship's future. Deep Space One showed the breath could be trusted. Dawn made a life around it, spiraling to Vesta, learning its wrinkles, leaving gently, and spiraling again to Ceres. No chemical stage could have threaded that itinerary. Ion drives do not make missions fast, they make them possible. The velocity they deliver is not the spike of a launch, but the long, steady rise of a tide. Looked at as a whole, the curve of speed has a shape we can name without sighing. The 1,960 seconds were a rocket's rising arc. After that, the gains thinned and matured. We traded raw pace for endurance, precision, and efficiency. We built tools to see and think better, to aim better, to use less, to do more. This does not mean surrender. It means we have pressed chemical combustion near its natural limits and learned that electricity, sunlight, and gravity give us new rooms to work in, but not jetpacks to skip the stairs. Speed is only one pillar. If you hope to live far from grocery stores and clouds, you must close your loops. Water must come back to water. Breath must come back to breath. Plants must trade with people in a circle that does not fray. On the International Space Station, we practice pieces of this: urine to drinking water, carbon dioxide scrubbed and oxygen refreshed, humidity caught and returned. But food arrives by ship, filters and valves arrive by ship, and quiet heroics from the ground keep everything tuned. We tried a rehearsal on Earth. In the Arizona desert, a sealed glass and steel world called biosphere. 2 held oceans, forest, desert, and fields. 8 people went inside in 1991 to learn how a tiny planet can keep itself honest. It did not. Oxygen dropped when concrete swallowed it, in chemical reactions no one expected to matter so much. Carbon dioxide spiked. Many animals, and most pollinators, vanished. The crew quarreled and coped and did their best. But after 2 years, the experiment told a humbling truth. A closed ecosystem is not a machine you switch on. It is a garden you must understand deeply. And our understanding was not enough. In a long mission, every leak compounds. A system that loses a fraction of a percent of its water each year looks fine in a quarterly report and becomes catastrophe across a century. Filters clog, plastics outgas. Trace contaminants play chemistry in the dark. Microbes evolve into little surprises. A design that works for an expedition must grow teeth to become a town. The open loop bring plenty, and toss what you're done with has served explorers for centuries. In space, distance and time make that loop cruel. Closing it is not optional, it is survival. People are loops, too. We carry minds that like seasons, faces, sky, green things, new vistas. Submarines, Antarctic stations, and orbital crews have taught us that humans can adapt to months away from crowds and weather. Around the 6-month mark, strain rises, sleep moves, moods swing, attention frays at the edges. We manage with schedule, light, exercise, purpose, and companionship, and we rotate crews. A Mars round trip presses this to its edge. 2 to 3 years where patience must be treated like oxygen. Stretch the canvas to a generation ship, and the canvas tears. We have no data for that life. Children born under a ceiling, never having known horizon or storm, might thrive differently than their parents, or suffer in ways we do not yet have words for. Would they inherit the mission as meaning, or as a debt? Ethics, then, step to the front. Is it fair to sign people up for a journey before they exist? A mission across 50 or 100 generations would ask strangers in the future to keep a promise they did not make. History on Earth is full of cultures that changed their minds in far less time, by choice or by pressure or by need. A ship is a small city with no hinterland. How do you keep its argument about direction from becoming a schism? Some plans sketch strict rules, a charter that binds every berth to the course. Others imagine constitutional protections for the mission amid free debate. Both accept a delicate paradox. You cannot guarantee obedience and still call it consent. At any point, the living may decide that continuing is not the right way to be alive. All of this may sound like gravity for the spirit, and yet it is air as well. Knowing the weight of the task lets us plan with care instead of slogans. The staircase becomes less of a mystery and more of a craft. We choose missions that fit our engines, and engines that fit our patience. We design habitats that cherish psychology as much as plumbing. We improve closed loops, one gasket at a time, and celebrate every % of loss shaved away. We practice redundancy that is generous without being wasteful, autonomy that is calm rather than reckless. We learn, slowly, to turn "can we survive" into "can we live well?" The history of speed, read in this light, is not a disappointment. It is a map where the contour lines are hard truths and the footpaths are the ways we have found to live with them. Orbit first, then out. Fire, then patience. Bursts that get you there, then long listening that makes there turn into a place with stories. Along the way, we keep learning that fast is only sometimes the answer. More often, the right word is enough. Enough to capture, enough to break, enough to stay, enough to study a storm from its first whisper to its quiet end. When you close your eyes and remember the arc, from Sputnik to Parker, from Gagarin to the station keepers, from Helios to Voyager to Dawn, you can feel the tempo the way a musician feels a time signature. 2 steps forward, 1 to the side, a rest, a crescendo, a diminuendo. Repeat. The melody is human, brave, fallible, stubborn, inventive. It is not a march to a trumpet's blare. It is a lullaby with a drum beneath it, steady and kind, telling us to keep climbing at the speed that keeps us whole. Out on the open water of space, navigation feels less like following a road and more like learning the tides. On Earth, you can glance at a map, catch a GPS fix, and trust that the landmarks are quiet and the coordinates are solid. In space, everything is in motion. Earth orbits the Sunday. The sun slides on its long path around the center of the galaxy. Nearby stars drift like buoys in a slow current. There is no fixed grid painted on the dark. If you mean to meet Mars, you do not point at Mars tonight. You point at where Mars will be after months of quiet acceleration and coasting, when your arc and its arc kiss at a single moment. The math that draws those arcs is not scenery, it is the ship. Mission designers begin with a simple picture and let it grow honest. The two-body problem, one mass circling another, gives orbits as clean as spun glass. Add a third body, and the glass shows ripples. Add Jupiter's tug, the sun's gentle oblateness, the press of sunlight on a wide panel, the hiss of outgassing from a warm tank, and you are keeping a ledger that never quite closes. Computers do the heavy lifting, but their answers are only as good as the measurements they drink. Ground stations listen to a spacecraft's radio tone and measure the Doppler shift to the millimeter per second. Deep space antennas catch the faint echo of a ranging signal and return a distance with a small uncertainty. Star trackers watch patterns in the sky the way sailors once watched the Pleiades, comparing angles to catalogs so the computer knows which way the ship is pointing. Gyroscopes carry that knowledge through brief, blind patches. All of it, together, becomes a posture and a plan. Far from home, delay enters the conversation. Commands sent today arrive minutes or hours later. By the time a rover hears "break," it has already chosen whether to swerve around a rock. Autonomy grows from necessity. Spacecraft learn simple, safe habits. If the star tracker is confused, stop thrusting and reorient. If sunlight spikes, take cover. If a wheel slips, slow the sequence and try a different path. Navigation is not only position, it is judgment at the edge of silence. Aim for another star, and the challenge stretches thin and wide. Stars have proper motion, tiny drifts across the sky that add up over decades and centuries. A target measured at 4.24 light-years today will not stand exactly there when your messenger arrives in some distant age. A mistake of 1,000th of a degree at launch sounds like nothing and becomes a miss by billions of miles. There will be no gas stations to course correct at. The fuel that gets you going must also be the fuel that lets you trim your path, and the price of a trim rises steeply with speed. The only cure is exquisite aim and clocks that do not lie. You must know the star's motion, its wobbles from any planets, the pull of neighbors, and the slow ballet of the local interstellar gas. Then you must engrave that knowledge into a trajectory and protect it from drift. If one day we fly at a meaningful fraction of light speed, the scenery itself changes. Time on board would pass slightly differently than time at home. Distances ahead would contract from the crew's point of view. Light from stars in front would shift toward higher frequencies. Light from stars behind would redden. The glow of the microwave background, usually even in all directions, would become warmer in the bow and cooler in the stern. None of this breaks the rules we use now. It simply asks our instruments and software to speak relativity as a native language rather than as a phrase book. Navigation would be a conversation between maps built on Earth and maps built on board, with careful translations at every step. Between the comfort of the inner system and the audacity of another sun, there is a middle distance that tempts planners with both difficulty and reward. Beyond 550 astronomical units, the sun's gravity acts like a giant lens. Light from a faraway planet bends around the sun and focuses along a long focal line that begins a little past that distance. A probe that takes up a careful station there could use the sun as a natural telescope. With the right sensors and steady pointing, an image of an exoplanet could, in principle, be reconstructed in astonishing detail. Not a single smear of light, but a disk with features. Oceans and continents would stop being guesses. Weather patterns could be watched. If lights shone in a pattern that was not natural, you might even dream, carefully, of cities. This is a practical kind of miracle. It does not demand impossible speeds. It does demand a long flight, stable power, precise navigation, and an eye that can keep its hand steady. How long is long out there? At the speed of Voyager, 550 AU is a human lifetime, plus a generous measure. With engines we already understand, sharpened by nuclear power for electricity or heat, a dedicated mission might manage that distance in a few decades. That is longer than most careers and short enough to be lived through. Along the way, the craft could test the arts we will need later, autonomous course-keeping over years, pointing that does not wander, low-noise communications that stay honest across the widest stage we have ever tried to use. As for what to send across greater darkness, the answer is not a single vehicle, but a menu. The golden records that left with Voyager were physical things that any patient mind might decode with tools and curiosity. They were human, in their limits, and in their generosity. Digital messages are lighter to carry and richer in content, yet they assume a reader who shares our conventions, who can guess our encoding and our math jokes. Genetic blueprints have their own elegance. Chemistry is a common tongue. A sequence written in bases and paired with clear instructions might be more universal than any greeting we can sing. And then there is the idea of sending minds that are not biological at all. An artificial intelligence, built to learn, to repair itself, to be small and tough and sleepless, could make the crossing more easily than any crew. If it could harvest local materials to build tools when it arrived, one seed could become many scouts. Seeds, however, require ethics. Self-replication is power with sharp edges. A bug becomes a bloom that cannot be stopped. A cautious probe might look like a threat to someone else, or someone else's cautious probe might look like a threat to us. Values placed in software can drift, like language in a diaspora. If we send such travelers, we are not only engineers, but authors and parents, deciding what principles must hold when the original voices are too far away to be heard. That is a responsibility to name directly. All these practical questions sit under a larger, older one. that has been asked at lunch tables and blackboards for generations. If space is full of worlds and time is vast, where is everybody? One simple answer says, we are running into the same wall others have met. Sublight speeds are not a moral failure, but a universal limit. Cross the galaxy at 10% of light and you need 1,000,000 years. Add time to build, to settle, to launch again, and even an ambitious, healthy culture needs tens of millions. Measured against the age of the Milky Way, that is not infinity. Measured against the number of cultures that may arise at different times, it is enough to leave long, quiet gaps. Perhaps we live inside one of those gaps, early enough that the seas are still mostly empty of ships. Another answer imagines a door in the physics we have not found, a way to fold distance or borrow energy that turns the map into something friendlier. If such a door exists and opens eventually for most minds, then silence here could mean most travelers graduate to a realm we cannot yet visit or even notice. It is a hopeful story that refuses to contradict the experiments we have run. It also asks us to live well, without the promise that the door will open on our watch. A darker answer holds a mirror we do not enjoy. Intelligence may be common enough, but stable wisdom may be rare. Civilizations learn to shape fire, find the atom, code the genome, alter climate, and then stumble. The span between making ships and making ruin might be short. The quiet, then, would be a field of fallen ladders. If this is the truth, our speed is not the problem, and our navigation is not the problem. Our task is to become old without destroying ourselves, to steer through our own storms first. Whatever the answer, the mechanics of finding our way do not change. We will keep building missions that aim not at a point, but at a time. We will keep treating gravity as both obstacle and tool. We will keep measuring, correcting, and teaching ships to make safe choices when a signal cannot arrive in time. We will keep simulating the N-body dance with better clocks and cleaner code. We will keep folding relativity into our software as speeds climb and views distort. We will keep sending pathfinders to middle distances where new perspectives are born. Each small success is a rung in a ladder we will need whether or not we ever run our hands along the grain of another sky. If you want to picture how this looks in practice, trace a flight. A small craft leaves Earth on a quiet electric push, spirals outward over months, meets Mars from the side instead of head-on, and slides into orbit without drama. It surveys, samples, and learns. Later, the same craft lights its thrusters and eases into a transfer toward the main belt, guided by faint starlight and the steady tick of its gyros. It times a meeting with an asteroid whose path is known to the second. It fires, pivots, and matches pace with a body the size of a town. It takes time because time pays for precision. When the fuel is right and the instruments have rested, it reaches again, this time toward the Trojan swarms that trail Jupiter, rich in ancient chemistry. The trip is not a sprint. It is a series of well-kept promises. Now step further and imagine a mission to the sun's focal line. The craft hurries while it can, rides a gravity assist, folds its sail or steadies its reactor, and settles in for a long glide. Course checks depend on a star field that shifts by hair widths. Communications become whispers caught on dishes the size of parks. When the craft finally enters the narrow cylinder where a distant planet's light is focused, its job is like a watchmaker's. It nudges, samples, integrates, and watches patterns grow out of noise. The first image is raw and strange. A ring or a line that makes little sense. With patience, algorithms turn those rings into a map. Somewhere in that map, Clouds throw shadows. Storms move. Something bright reflects off a calm sea. The mission sends home not just data, but a lesson about what distance can give when speed is modest and care is large. In the end, space navigation at the speeds we can make now is an art of humility. You accept that the universe will not meet you halfway. You accept that targets move, that errors grow if left alone, that course changes are expensive, that clocks must be faithful, and that knowledge ages. You design as if your grandchildren will need to understand your choices. You teach machines to be calm when they do not hear from you. You pick paths that give you room to breathe. You keep a little fuel for grace, and you let the slow, steady march of better instruments, better methods, and better judgment be the real acceleration that moves us quietly and well toward the next shore. There is a strange comfort tucked inside Einstein's equations, a soft kind of hope that only shows itself when you go very, very fast. Time itself loosens a little. From the couch on Earth, a ship near light speed would seem to crawl through years. Inside the ship, clocks would yawn and slow. The crew would feel fewer years than those who waved goodbye. At 9/10 of light speed, ship time runs at a little less than half the rate of home. Push closer 99%, 99.9, and the difference grows dramatic. A star that looks a decade away from Earth's calendar could, from the traveler's perspective, fall within a handful of years or even months. The price, of course, is a one-way ticket into the future. Every trip cuts the ties to the moment you left. Friends age, cultures turn a page. You return to a home that has moved on without you, or you never return at all. For robotic messengers that carry no birthdays, this is irrelevant. For people who carry anniversaries and lullabies, it is a tender ache. And there is the harder truth. We cannot yet buy the kind of speed that makes time dilation a practical balm. The energy bill climbs like a cliff. Even in an ideal world where every joule becomes motion, nudging a massive craft toward 9/10 of light demands fuels and engines that we do not have, plus a way to push the fuel you are carrying without needing yet more fuel to push the fuel. The math refuses to be charmed. Our current craft, heroes that they are, play at the lawn's edge of relativistic effects. The promise is real. The distance to that promise is, too. All of which leads to the quieter question that decides whether promising equations ever leave the page. Who pays, and why? Nations build space programs for reasons that travel in company pride, security, scientific hunger, jobs, diplomacy, the wish to be seen as capable and kind. During the Cold War, a rivalry powerful enough to tilt budgets towards Saturn V rockets gave us footprints on another world. When that rivalry eased, so did the river of money that only geopolitics can summon. Crude programs now thread needles between ambition and appropriation committees. Stations are maintained. Lunar plans experience the seasons of delay and restart. We are not stingy. We are human, and our needs are many. Private companies have changed the tempo nearer to home. Lower launch costs turn hard no into maybe, and maybe into yes, for satellites, cargo, crew rotations, and telescopes. Competition trims waste and sharpens schedules, but markets like projects with visible return, an interstellar probe that pays back in wonder rather than cash flow, does not fit neatly on a balance sheet. Tourism to orbit has a price tag and a customer. Mining water on the moon to sell propellant has a buyer. A generation ship has shareholders only if we change what return means. Historically, governments handled the missions that could not promise profit polar traverses great observatories, basic science, and the dividends arrived as knowledge, capability, and national character. If governments step back and companies stay pragmatic, the hardest propulsion dreams live in the gap between public good and private incentive. One bridge is the same one we use to build a station you can see from your backyard at dusk. We do it together. The International Space Station is a quilt of modules, wiring, languages, and traditions, stitched over decades by people who often disagree on everything else and still agree to share air. The same spirit could carry a fusion propulsion program that no single country can justify alone, or a mission to the sun's far focus where the payoff is a portrait of another Earth. Cooperation spreads the bill, the risk, and the pride. It also spreads the danger of drift. Elections change priorities. Economies slow and surge. News cycles stutter. Space moves at the pace of ice sheets and forests. It asks politicians to think like grandparents. When talk turns to crossing the long dark with people on board, using speeds we can plausibly earn, the mind arrives sooner or later at generation ships. Not a vessel, exactly. A small world, kilometer scale. Rings or cylinders that pretend to be gravity by spinning. Farms that sip light and water and return food and air. Fish, bees, microbes, trees, wheat, and the quiet choreography that keeps an ecosystem honest when it has no wilderness to borrow from. Workshops that birth spare parts, schools, clinics, music, law. The list grows until you realize you have written down a city with no surrounding country, a town that must be complete on launch day because there is no truck coming from the next county with potatoes and wire. Ecology, inside such a drum, is not a backdrop, it is engineering. Too many herbivores and the fields fail. Too few pollinators and next season vanishes. Disease in a keystone species becomes a systems failure, not a sad entry in a park ranger's log. Earth's ecosystems are resilient because they are broad and full of redundancy. A ship's ecosystem is thin and delicate by comparison, thousands of linked loops that must survive the coughs and surprises of centuries. We will need a gardener's humility and a mathematician's patience to design such a place. And even then, life has a way of improvising past our best guesses. Government aboard is not simpler. Consent is a verb that must be repeated, not a contract signed by the long dead. Democracy permits a turn of the wheel. A later generation can vote to settle on a passing world or to stop and build a ring of stations around a resource-rich comet. A charter that forbids this begins to look like a cage. Authority that insists on stay the course at any cost flirts with oppression. Revolt tears missions apart as effectively as micrometeorites. Some dream of a hybrid, a constitution that protects the mission's bones, safety, continuity of the ecosystem, the sanctity of air and water, while letting culture and leadership renew. That is beautiful and brutally hard. Most human institutions erode or ossify long before a millennium has passed. Religions and songs last. Bureaucracies and parliaments molt or die. Culture will wander anyway, because culture is alive. Language slides vowels. Stories change endings. Holidays drift. Children born under a painted sky will grow their own metaphors. The founders' speeches will become liturgy or comedy or homework. This is not failure. It is what humans do. The question for a mission is not, how do we keep them the same? But how do we let them become themselves without losing air, water, and purpose? If the arrivals, 500 years hence, speak a language we cannot parse and hold beliefs we never imagined, and still gently break into orbit around the target star with a healthy forest and a cheerful school, the mission will have worked. Genetic engineering stands at the edge of that conversation like a tempting tool on a bench. Make bones that laugh at radiation, tweak metabolism so calorie needs shrink, extend life so a person can be child, worker, elder, all on one voyage. Each change reduces a burden on the hull and power plant. Each also walks us, step by reasonable step, away from the body that wrote symphonies and treaties on Earth. Where is the line between adaptation and invention of a new species? And if we can turn down fear or widen patience with edits to temperament, should we? A ship full of people engineered to be content in rooms with no horizons may function. It also may be a beautiful prison. Dignity matters, choice matters. Engineering compliance is not stewardship, it is abdication. Some would bypass flesh entirely, copy a mind, store it in radiation-hard memory, and send it wearing a chassis of ceramics and carbon. Let the traveler sleep at microwatts and wake to work at another star, self-repairing, unafraid of vacuum. A digital person could speed, idle, compress subjective years into mission months, or slow to a crawl when there is nothing to do. The engineering might even prove easier than keeping a city alive. The philosophy does not yield so quickly. Is the copy you? If your body dies on Earth and your pattern wakes under Alpha Centauri's light, did you travel or did you send a clever heir? For some, a copy is continuity. For others, it is legacy, not identity. The difference is not academic. It decides whether "we went" is true. Beyond ships, drives, and minds lies the climate in which decisions get made. Political economies tilt toward the immediate. Space punishes the rushed and rewards the steady. The compromise is to choose projects that make sense at every scale. Telescopes that serve Earth and also teach us how to build eyes for deep space. Propulsion work that first trims travel time to Mars and later scales toward the Kuiper Belt. Deep space communications that help farmers and firefighters today while training teams to whisper across a light day tomorrow. When budgets tighten, the projects that survive are the ones that return value early and often, even as they lay stones on paths that lead far. There is, finally, the question that sits like a companion at the edge of every campfire story about the stars. If the universe is old and big, and the chemistry of life seems generous, why is the sky so quiet? Maybe the speed limits we keep meeting are not parochial but universal. Maybe everyone crawls at first, learns to walk, then jogs, and only a few societies ever sprint, and not for long. Crossing a galaxy at 1/10 of light speed takes 1,000,000 years. Filling it with settlements and shipyards takes longer. Measured against 13 billion years, that is short. Measured against the brief brightness of cultures, it may be too long for most to stay coherent. Perhaps we are early, and the sea is empty by youth rather than by doom. Or perhaps the sea is cynical. Many launch, fewer arrive, and most extinguish themselves in ways that have nothing to do with physics. Whichever story proves true, the practice of going faster and farther is, paradoxically, an art of going gently. Relativity offers a promise we may use one day. Until then, our work happens at the speeds we can afford, designing engines that run cleanly for decades, learning to close ecological loops until waste becomes resource, writing software that chooses caution without drama, crafting institutions that hold a mission without crushing those who must live inside it. We learn how to share the bill and the credit. We remember to plant missions like trees, in the right soil, with guardians who water them, and with the humility to accept that someone else may one day sit in their shade and call it home. If that sounds slow, it is. Slow is not failure. Slow is a tempo that keeps hearts safe, ecosystems balanced, and promises intact. Time dilation belongs to the far lane. Patience is the engine we have now. With it, we can make honest miles across the cislunar neighborhood, out to Mars in healthier spans, around the giant planets with instruments that linger, into the Kuiper Belt with reactors that hum softly, and, when the sums and the will align, toward the sun's far focus to paint the first clear portrait of another blue world. When the night is quiet and the sky is kind, this feels like enough to know the rules, to play them well, and to keep reaching, unhurried and steady, for the next star over. Begin by standing on the nearest shore and looking outward with clear eyes. The first islands in that dark sea are the stars we already whisper about by name. Proxima Centauri, the neighbor whose light is a red ember, hosts at least one world in the temperate zone where liquid water could, in principle, linger. It sits a little over 4 light-years away, a distance close enough to imagine and stern enough to humble. At the pace of our elder voyagers, the crossing would take on the order of an ice age. At the pace of the boldest near-term concepts, say a few percent of light speed, it would still be a story told across several generations. And Proxima is moody, a flaring red dwarf that bathes close planets in bursts of radiation. Habitable perhaps in sheltered oceans or under rock. Harsh, certainly, on any open shore. Nearness is not the same as welcome. Just a touch farther is the whole family of Alpha Centauri, A and B, stars not unlike our sun, with Proxima tagging along light months away. If friendly worlds circle anywhere nearby, this is our best bet. Stable light, familiar warmth, orbits that could cradle seas for a very long time. The distance, though, remains a test of patience. With propulsion we can describe but not yet fly, the trip would be measured in human generations, not school years or careers. You would launch, knowing your grandchildren might be the ones to read the first proper "we have arrived" message. Hope and logistics would need to share a room and learn to get along. Widen the circle and new names appear. Barnard's star slides quickly across our sky, the sprinter of the neighborhood, though the worlds some once imagined there remain uncertain. Wolf 359 glows faintly, a quiet red more likely to punish than to comfort a surface ocean. Sirius dazzles our winter evenings, but dances tightly with a white dwarf companion, a waltz that complicates calm, long-lived orbits. Tau Ceti sits out there with hints of multiple planets and a sun-like face, yet it lies far enough that even brave percent of light ideas turn the voyage into centuries. Within 20 light-years, the catalog grows busy, and the map feels kinder. Dozens of stars, perhaps hundreds of worlds, but the arithmetic stays honest. Distances stretch, and even our best imagined speeds turn the dots into commitments rather than trips. When people wonder how a truly advanced culture might tip the balance, they often reach for the picture of a Dyson swarm. Not a solid shell. No civilization we can sensibly describe would build that, but an airy ballet of countless solar collectors sipping a star's light and turning it into work. With that kind of power, pushing sails with lasers or feeding hungry fusion engines becomes ordinary labor instead of myth. The fact that we do not plainly see such swarms in our surveys may mean they are rare, cleverly disguised, subtle in their waste heat, or simply built in ways our instruments have not learned to notice. Absence, here, is a whisper, not a verdict. If we ever stitched even a modest fraction of such a swarm around our own sun, the energy available would make today's grids feel like campfires. That river of power could drive beams to push wafer-thin sails toward surprising fractions of light speed, warm factories in cold orbits, and feed life support for entire cities that live in permanent shade. But the work list is planetary, mining worlds into girders, building and aligning trillions of machines, and keeping the choreography intact across decades and centuries. Before you can harvest a star, you must already be at home in your system, moving raw material, closing life support loops, and trusting your tools to behave for a very long time. As our reach lengthens, autonomy shifts from luxury to necessity. The farther we go, the slower our conversations become. Spacecraft will need to steer, schedule, troubleshoot, and sometimes decide what counts as interesting without waiting for permission. A probe that spends years between signals must carry good judgment as surely as it carries power and thermal control. We can tune that judgment with goals and guardrails. We can teach an explorer to pause for safety, to save data when storms hiss, to retry gently when a valve sticks. What we cannot do is pilot from a blue planet away and expect to be on time. For any messenger sent beyond the easy cadence of back-and-forth radio, independence is not a feature, it is breath. That responsibility widens when we imagine machines that can make careful copies of themselves. A single seed probe that harvests local resources and builds a few children could, over centuries, sketch a lacework of exploration paths across the map. But a software bug becomes a bloom. A poorly chosen objective becomes a gray garden that someone else might rightly fear. Governance for such explorers is not an afterthought. It is the first line in the design document. We owe the galaxy neighbors, who may exist, the same caution we ask for ourselves. In practice, that means hard limits, audit trails, kill switches that cannot be disabled by clever updates, and values embedded in code that privilege restraint over appetite. Back inside the sun's long reach, our speed is tied to a quieter word: logistics. Launching every kilogram of fuel from the bottom of Earth's deep well is like starting a cross-country trek with every meal for a year packed into the trunk. You can do it, but you will not love the drive. In situ resource utilization changes the posture. Water ice in shadowed lunar craters and inside certain asteroids can become oxygen and hydrogen. Carbonaceous rocks hold volatiles. Chemistry can turn into propellant and plastics. Tanks filled in space do not pay the gravity tax. A ship that tops off at a depot in cislunar space leaves Earth lighter, leans on smaller rockets, and arrives with more muscle left for braking, orbit changes, and science. Imagine the moon as a workshop and way station. Its gentle gravity lets cargo rise on a whisper compared with Earth's shout. Regolith becomes aluminum and glass. Ice becomes propellant. Sunlight becomes the hum in a smelter. Add printers that work like quiet spiders laying down trusses, and simple foundries that pour beams. From there, Mars is not just a dream. It becomes a leg of a route. Mars, in turn, is both destination and springboard. Lower gravity than Earth, a sky that can host power with the right engineering, and resources that turn into plastics, metals, gases, and fuel, make it a factory as well as a frontier. A mission that launches from the moon, refuels near Mars, and heads for Jupiter or the Belt begins to look less like a stunt and more like a schedule. Asteroids are the corner stores on this route. Metal-rich bodies offer nickel, iron, and useful trace elements. Carbonaceous ones hold water bound to minerals, plentiful volatiles, and organics that chemistry loves. Small robot-run depots can crack, chill, and store propellant. Larger outposts can print tanks, booms, radiators, and simple engines. Communications relays drape the lanes with a steady signal. Navigation beacons give autonomous ships the confidence to thread crowded spaces. None of this is a single triumph with trumpets. It is 100 patient victories at the scale of valves, seals, solar arrays, and software patches that never make the news and are, quietly, the difference between hope and habit. When infrastructure thickens, speed follows, not because any single engine becomes magical, but because the system removes drag. You no longer overbuild a launcher for the worst day in a decade. You no longer insist that a transfer vehicle carry both outbound and return propellant, just in case. You no longer throw away a spacecraft after one target because you cannot afford the Delta V to change plans. You move like sailors who know the ports and the winds, confident you can resupply, repair, and reroute without drama. Practical velocity rises because each leg is lighter, each burn smaller, and each itinerary more flexible. Even with such a network, choosing where to go first remains an art. Alpha Centauri will always sing because it is near, bright, and kin to our Sunday. Proxima will always tease because it is nearest, even if its temper makes surface life tenuous. Tau Ceti will keep its quiet promise just beyond the comfortable line. The truth is simple and kind. We will not pick a single first star and lay all our bets there. We will send many small scouts with different talents, spectrometers, magnetometers, tiny imagers, sniffers for dust and gas, because redundancy is a form of respect. Some will fail. Some will find nothing headline-worthy and still teach us what not to try next. A few will open doors we did not know how to knock on. Meanwhile, the sun itself can help us see what we cannot yet reach. Far beyond Pluto, along a narrow focal line that begins a little past 500 astronomical units, the sun's gravity acts as a lens. Light from a distant planet bends around our star and comes to a kind of focus. A probe that holds station there with careful thrust could use that natural telescope to reconstruct an image of an exoplanet with astonishing detail. Perhaps oceans and continents instead of a single pale dot, weather patterns instead of a hint, maybe even bright lines that should not be there if there is anyone to draw them. Such a mission is hard in the way that good engineering is hard. Precise navigation, honest power budgets, detectors that keep their promises, patience that does not blink. It does not require a miracle. It requires craft. Across all of this, artificial intelligence becomes the quiet crew member that never sleeps. We will ask it to dose autonomy responsibly, enough to keep a ship safe and curious when the line to Earth is thin, never so much that it forgets the rules we wrote together. The questions are not hypothetical. If a probe reaches another star and sees something that looks like a transmission, does it answer? If a landing site changes between surveys, does it risk a bolder approach? The delays at interstellar scales make ask home into a ritual rather than a real-time option. We will need software that can say not yet to itself, and architectures that keep a mission aligned with human values for as long as the mission lasts. All this talk about engines and targets circles back to a quieter insight. Speed in space is a system, not a switch. It lives in propellants and power, yes, but also in depots. Docs, standards, training, and trust. The more we stage fuel beyond Earth, the more we manufacture off-planet, the more we let AI steer inside well-drawn lines, the more our practical velocities rise. Build a handful of fuel depots, and you shave months from schedules. Build a dozen, and you rewrite what reachable means. Teach 100 small craft to sail sunward for power and outward for work, and you turn the outer system into neighborhoods instead of distant postcards. So the path ahead is simple in outline and rich in detail. Seed the cislunar economy with power, communications, and propellant. Put small refineries and depots where the math is kind. Practice on nearby asteroids until the wrenches and software feel like muscle memory. Stand up a steady cadence of launches that feed this network instead of one-off epics that end with parades. Test autonomous pilots on trips that last years, not weeks, with watchdogs that know the difference between initiative and drift. Aim a patient mission toward the sun's long lens and give it the tools to draw what it sees. Let 100 tiny sails go and accept that many will fail gently. The few that succeed will teach in a way no single flagship can. In that world, a mission to the outer giants is not a rare once-in-a-decade event, but a line on a calendar. A Kuiper Belt tour is a fellowship more engineers can apply for, not a once-in-a-lifetime lottery. A scout aimed at Alpha Centauri is audacious but not absurd. We will still be slow by the measure of light. We will be fast by the measure of history. And as our network grows, the decision to try for the nearest suns will feel less like a leap of faith and more like the next careful step on a well-built road. Microgravity changes a body in slow, insistent ways. Bones that grew strong under 1G begin to thrift their minerals. Without the tiny stresses of walking and standing, calcium drifts back into the blood and the lattice thins. Think of it as a whispered negotiation between skeleton and space. About 1% of bone density can fade each month if nothing is done. Muscles answer to the same logic. Calves, quads, the deep postural bands along the spine, they all lighten their load when up disappears. Fluids shift toward the chest and head, puffing the face, pressing gently on the eyes, sometimes nudging vision in ways that linger after landing. Hearts, freed from the daily climb against gravity, relax a little too much. The cardiovascular system grows modest and unambitious. After half a year aloft, even the fittest astronaut steps onto Earth, needing weeks to meet stairs like an old friend again. Now stretch that to a multi-year Mars voyage, a long stay on a world with just 38% of Earth's pull, and the concern sharpens. Arrive too deconditioned, and the first tasks on red soil may be harder than they should be. Come home after years away, and the return itself is a test. One answer is to bring gravity with you, not by changing the universe, but by using its geometry. Spin a habitat, and the outward push of rotation mimics weight. In a ring or a pair of tethered modules, feet down, head up, a body gets back many of the cues it grew up with. Bones keep their bargain, muscles keep their tone, yet rotation writes its own rules. Turn too fast, and the inner ear becomes a trickster. Pour a cup, and the stream curves. Turn your head, and the room swims. To make the Coriolis mischief small, you want a large radius and a gentle rate, wide circles, slow turns. Wide circles mean mass and structure. Mass asks for stronger engines to accelerate and decelerate. Stronger engines ask for more propellant or more power. A generation ship that spins comfortably for decades is, by definition, large. and large things are stubborn about changing speed. Every solution tugs on another thread. Radiation is the other weather you pack for. The sun sends flurries and storms. The galaxy sends a steady, patient sleet of high-energy particles born in ancient violence. Earth's field and air make these showers into drizzle. Out there, hulls do the work, and thin ones do not catch enough. Lead is heavy, and heavy is unwelcome. Water and plastics rich in hydrogen, slow cosmic rays, more kindly per kilogram. And water is something you want anyway for drinking, for oxygen generation, for plants. Stack tanks around a sleep nook, and you get a storm shelter where a crew can wait out a solar tantrum. Layer walls with polyethylene, tuck supplies where they double as armor, and you buy margin without waste. Magnetic shielding tempts with the image of a ship wearing its own magnetosphere, but strong fields and their power sources bring heat, complexity, and new failure modes. Every kilogram of safety competes with every kilogram of science and fuel. You do not choose once, you balance always. Mines need shielding too, but of a different kind. Long missions begin like summer camps, all camaraderie and purpose. Then the middle months arrive, and small habits, an unwashed mug, a loud laugh in the quiet hour grow thorns. Sleep drifts off rhythm, dreams become busy. A few people withdraw, a few spar. Most teams find their groove again with clear routines, private corners, rituals, and honest check-ins. Some never quite do. A Mars expedition at 2 to 3 years pushes the edge of what we understand about isolation. Longer journeys would ask for richer social ecosystems, larger crews so friendships can ebb and flow, spaces that change light and color with the day, work that engages hands and minds, libraries of art and music and sport, and counselors who treat care as maintenance rather than repair. Every added person brings mass, air, water, food, and a vote. Every empty seat brings risk of monotony and brittle dynamics. The ledger keeps its columns. Green life softens the edges. A tray of lettuce under full-spectrum lamps is more than calories. It is smell and color and the quiet company of growth. Hydroponics and aeroponics replace soil with films and mists, but they still need light, water, nutrients, and air that moves. In microgravity, roots do not know which way to search. Leaves can overheat without convection, and pollen refuses to fall. Fans, baffles, and clever geometry become the farmer's winds and slopes. Pest control is not an afterthought. An outbreak in a closed loop is not a nuisance, but an event. Beneficial insects, quarantines, and rapid response plans sit beside seed catalogs. Grow lights sip power day after day. Pumps hum, filters clog, humans weed. Agriculture is comfort and competence braided together, and every kilogram of greenhouse is another kilogram you must push. Some sketches try to skip the hardest part of time itself. If a crew could sleep like bears through winter, metabolism cooled, needs humbled, then months in transit would pass with little strain on supplies or patience. Medicine has coaxed animals into torpor. Humans do not yet have that switch. Even if we find it, muscles and bones wither faster in deep rest, unless the body cycles some simulation of load. Waking must be gentle and safe. Minds must come back sharp. The margin for error is thin when your hospital is a small room with humming pumps. Colder dreams, true cryonics face ice crystals that rip cells like tiny knives. Cryoprotectants help but bring their own poisons and limits. Some frogs and insects cheat death with sugars and proteins we are only beginning to understand. Whole, healthy humans are another scale of problem. None of this is forbidden by physics. All of it is stubborn in biology. Design, then, becomes the art of trade-offs. A light ship can leave quickly, change course with grace, and arrive with fuel to spare, but has little room for gardens, thick walls, and big crews. A heavy ship can cradle people kindly for years, but demands oceans of propellant and power to start and stop. Navigation precision fights with shield mass. Redundancy fights with elegance. Autonomy fights with the wish to keep hands on the wheel from home. Mission planners do not optimize a single number. They tune a chord. Good enough, across many dimensions, beats perfect in one and brittle in the rest. History can be a lantern. Early ocean crossings were brutal. Crews vanished into scurvy and storms. Maps lied. Captains guessed. And mutiny was a word everyone knew too well. The ships that made it were not dramatically faster than those that failed. They were better built, better supplied, and better understood. Citrus and sauerkraut, star tables and chronometers, hull designs that forgave a sailor's mistake, incremental, unromantic improvements turned adventures into routes. Space will rhyme with this. We will not wake one morning to find our speeds multiplied by 10. We will wake to find water recycling that fails less often, exercise regimes that really keep bones honest, radiation forecasts with fewer surprises, greenhouses that run on fewer watts, and software that catches problems while they are small. Reliability is its own kind of speed. Still, interstellar distances write a different scale on the page. Even with craft we can plausibly build and engines we can plausibly light, journeys to the nearest suns live in decades and centuries. The switch from daring to routine that shrank oceans may never truly arrive between stars. Perhaps the best we can do is make the attempt survivable, repeatable, and meaningful, knowing it will always be at the edge of what a civilization can shoulder. Or perhaps some quiet theorem will open a door we have not seen. We cannot plan on that. We can leave a chair for it at the table. Admitting limits is not surrender. It is how you hold the map correctly. We cannot make gravity appear. We can spin what we build. We cannot make radiation kind. We can choose materials, layouts, and protocols that meet it with grace. We cannot make loneliness vanish. We can design communities that breathe and grow instead of merely persist. We cannot make time shorter. We can fill it with work that matters and rest that heals. That is not settling. That is craft. The universe is patient. Stars take their time. Galaxies circle slowly and never hurry. When we match that tempo, our work becomes calmer and truer. A slow ship can still be a good ship. A mission that arrives with a crew healthy in body and steady in spirit is a success, even if its velocity would not impress a beam of light. The voyagers will drift longer than our names will be remembered and still count as triumphs of the human hand. The station has turned sunrises into a metronome for more than 2 decades and taught us to live gently, where air is a decision, not a birthright. Mars rovers have aged into elders and kept walking until the sky itself asked them to sleep. None of these feats are fast. All of them are honest. So we keep weaving, exercise devices that keep bones loaded without breaking schedules, compact centrifuges where crews can nap in 1G for an hour and give tendons a memory to hold, water walls that double as art and armor, lighting that tunes circadian rhythms, Green corners where hands get dirty and minds get quiet. Selection and training that prize kindness alongside skill. Software that tells the truth early and without drama. Emergency drills that feel like choreography rather than fear. Each thread is small. Together, they become a ship that moves through years without losing itself. Someday, crossing the solar system may feel like sailing between well-known ports, not quick, exactly, but routine, tickets purchased, cargo booked, arrivals greeted with yawns and hugs. Between stars, the scale may never bend to comfort. That is all right. We were never promised easy. We were given rules, time, and curiosity. If we walk within the rules and give the work the time it asks, curiosity will do the rest. We are already learning to live off Earth for months. We are already growing lettuce under artificial suns. We are already catching and softening the rain of radiation with smart walls and smarter plans. We are already writing the etiquette of small communities in large emptiness. Hold that thought like a warm stone in the hand. Our speed may be modest, but our learning is quick. Each careful fix, each lesson about bodies and minds in weightlessness, each improvement in closed-loop life, each kinder habitat makes the next mile easier. Not easier to physics, but easier to us. And that, in the long run, is how hard things become possible. One gentle, honest solution at a time, carried forward by people who know that patience is not slowness. It is speed you can live with.